Okay, for this video, I'll be going through thermal properties of metal tutorial, question 2. Okay, a kettle with a 500 watts heating element, so this is my P, contains 1.5 kg of water, is left to boil. Okay, so this is my mass of water, and this mass of water is left to boil. That means it's already at 100 degrees, and then it will just start boiling. Okay. Oh, sorry. I'm wrong here. Okay. If the initial temperature of water was 20 degrees, how long does it take before the kettle dry up? Okay. So it means that if I were to draw a heating graph, okay, initial temperature was 20 degrees, and this is my temperature versus time scale graph. So if the water is 20 degrees, and if I heat it in the kettle, the temperature will increase. So it will increase until it reaches 100 degrees, and then it will be a flat line whereby it starts boiling. Okay, it starts boiling. And at the end of this time, okay, all the water has boiled off. And the kettle will then be dry up. Okay, so we need to assume that all the energy by heating is being transferred to the water. Okay, so over here will then be my CW or C liquid, right? Because we'll be using specific capacity, whereby over here there's only one state, which is the liquid state. Then here we'll be using LV, specific latent heat of vaporization, okay, whereby the liquid is changing into gaseous state. Okay, so there won't be any change in temperature. So using the formula, Q equals to MC change in theta, and the formula of Q equals to MLV. Now Q equals MC change in theta we'll be using for this stage. What is the amount of energy needed? The mass is 1.5. The C, we will need to use this 4200, which is a specific capacity of water. And the change in temperature will be always using the larger number, subtracting by the lower number. So it will be 1.5 times 4200 multiplied by 80. And this will give me a certain joules. Later on, I'll be doing the calculation. Now, for the second part, there will also be energy being transferred to the water. Oh, sorry. Yeah, to the water. And eventually, it causes the water to all become steam. So the mass of water or steam will still be 1.5. But now, I'll be using LV, which is the specific latent heat of vaporization of water. So it is 2.2 times 10 to the power of 6. Okay, and then I'll be having this amount of energy. So let me do the calculation now. Okay, so I have already done my calculation. So you see that the energy transferred to the water during when the temperature is increasing is 504,000 joules. Okay, for when the energy that's being transferred to boil off the water at 100 degrees is 3.3 million joules. Okay, so we gotta add up the total energy. So the total energy will be will be 504 plus 3.3 million joules. So this will be the total energy required, right? Assuming that all the energy is being transferred to the water. Now they are asking for the time taken, right? How long does it take? So we are looking for time, and we haven't used this physics quantity of power. And as you know, energy equals to power times time. So in order to find my power, I will need to have the energy that is required to be, in order to find the time, I will need to make T the subject of the formula. So I will have energy over power, which is actually this 380 for 000 divided by 500 watts, and the answer will be 7608 seconds. Then of course you convert it to 3SF, 7610 seconds. Okay.